So now we have question 4, assignment 3, question 4a. So you've got a mole of 1 mole ideal gas, it's 300, it's reversible and isothermal, compressed 25 to 10, blah, blah. Calculate these 3 delta S's. So to draw a picture and figure out what we're doing here is, you can imagine you start out at 25 liters and in there you've got 1 mole of gas, and the reversibility is the idea that the change in the volume takes place very slowly and equilibrated. So you put 1 grain of sand on, this little piston will go ever so slightly, then you wait for heat to flow one way or the other as is required. Anytime you compress an ideal gas, the temperature of it would go up, but then you wait. So let's say that this gas, after 1 grain of sand, went up to 300.000001. Well, then you wait. So that 0.5 zeros and a 1, a little bit of heat goes out to the surroundings, right? And the surroundings is viewed as this infinite heat sink that stays at 300, and therefore you wait for this gas to return back to the perfect 300. Then you put another grain of sand on, and very slowly equilibrated you do this. So that's the reversibility. Isothermal means you're letting any tiny increment of temperature of your gas going up because you're compressing it, that little bit of heat to transfer out. So going from 25 down to 10, obviously there is a total amount of heat, tiny little bit for each grain of sand you add. So there will be a total amount of heat for this process from start to finish that went out. Now, we've learned earlier in chapter 2 that technically if somebody asked you to calculate the work that was done during this process, we could have previously calculated that. So we'll come back to that in a second, but let's start with one of the things we know, and I'm just going to pick. Remember how there's 2 ways for the system. It can be done as a function of V and T. Could have been done as P and T. Since they gave us V, you just go ahead and I'm going to use that. So we had something that looked like this as our differential equation. Now remember that this form, we just left the number of moles out for the time being. If you're given a number of moles, you simply multiply either one of these when you get down there, because both of these at the moment would give you units of joules per K per mole. If you have the number of moles, you multiply and get rid of them. So, but this is isothermal, which means this is 0. So technically your system change in entropy, that is gone, and you're left with RT dV. If you integrate both sides, you get the change in entropy of the system, and this has to get integrated from V1 to V2, R over V dV. The R comes out, and that will be the integral 1 over V dV. This is in your notes, that's why I'm speeding this up a bit, just to run through it again. V1 to V2, so and we can throw in number of moles if we have it, and we do, so we'll put it in ln V2 over V1. So from your notes, you already had both of these would be in a formula box, but only one of these 2 terms will be left standing if it's isothermal, because that's 0, so that one's gone. So we're left with this. So for our question, you could use this. And that will give you an answer in joules per K. So that's for the system. So then what we realize is, because it's reversible, is it not true that, think bubble, the change in entropy of a system, one of the other fundamental definitions is the heat over a reversible path divided by the temperature. So by definition, anytime you calculate the change in entropy of the system, you always have to calculate some quantity of heat on a reversible path from beginning to end. This one happened to be reversible. So what's interesting is, we talked about how the surroundings, you actually use whatever the actual heat of the process was, but because you're the surroundings, you will use the negative of your system's point of view. So whatever the heat of the process actually was, you take the negative of it, divided by the temperature of the surroundings. So would we all agree this process was in fact reversible, so the actual heat of this process is going to be equal to that one. And we also already knew that by default, the change in entropy of the universe, or other books will use total, you add the two. That was surroundings I wrote there, so this would be system. Now, a couple of things we knew. Delta S total, or the universe, is always equal to 0 if the process was reversible. So how do we make this 0? Well, these two have to be equal and offsetting, but this is what this already tells us, because the quantity of heat transferred was the same because it was reversible. So whatever your number here was, it'll surroundings, so what? Let's think about it. What happened? Heat, when you're compressing this, transferred out to the surroundings. So the system, the quantity of heat from its point of view was a negative number over T of the system, which by the way was 300 Kelvin. Whatever that quantity of heat happened to be, the surroundings gets the negative of the system's value, which means the positive number divided by 300. So you see how they're equal and offsetting. It goes to 0. So you can see how part A, this gives you the numerical answer you need. The surroundings will be the opposite sign of that one. Adding the two together gives you 0. Now, just as a quick add-on here, and you should be ready for this on your test, we could just as easily add on things like this. You know, the same question. Is it not true that you've already done questions like this in chapter 2? Cover this for work, delta U and delta H. So not a bad idea to just tack onto this and say, how would I calculate work? And technically, what if you wanted heat as well? So I would say that the definition of work, we already know from a formula in a box. The gas. Remember how the pressure external in this reversible process, the external pressure is always very much the same as the gas. So you can replace this and integrate and get a formula that looks like this. So you could calculate the work for this process, which is basically, see this? You're simply, you're going to multiply that by T. And see how the units of entropy, the units are joule per K. So see how the work is going to be basically the entropy of the system if it's reversible and the same, multiplied by T. So that would be the work. Because it's isothermal and reversible, we also know if the temperature of an ideal gas does not change, guess what we know about delta U? For an ideal gas, delta U will be 0. Delta H will also equal 0. There'll be no change in enthalpy. And then the heat will equal the negative of work. So that handles that pretty nicely. A little bit of an add-on there. So now we can move on to, all right, let's try 4B here. So we're going to draw a picture of this one. I got to reread this and start this. Previous take did not work. Question B. It's essentially the same as A, with one difference. It's not going to be reversible. And it talks here at length to make sure we understand. You start out at 25 liters. You will end up at 10, just like we did in A, and the temperature stays the same. However, it's almost as if they put a weight on the top of the piston here. And maybe they had a pin stuck in the piston. They pull the pin so that it compresses it all in one single step. There's no equilibration, no reversibility. That's basically the biggest difference. And the final pressure of the gas equals whatever the external one was. So to capture this idea, we should put it in a picture. And we know it's 25 liters. We know it's 1 mole. And let's just, do we know the pressure? So maybe what we could do is from part A, what we knew was the final pressure, because as an ideal gas, the final pressure from part A, we had 1 mole of gas, that was 300, so it'd be 1.08206, 300, and the volume was 10 liters, right? So that's coming out at 2.462 atmospheres. So from part A. So what they're telling us is, let's pretend we put a pin holding it, and we somehow make sure that the external pressure on this, and maybe it's like a weight or some damn thing like that, the external pressure is going to be, oh, that's the initial. No, I got that right, that's right. So even though we're starting at 25, so I'm confusing myself here, I'm not saying that the initial 25 liter container, it's not at this pressure. This is where we're gonna end up down at 10 liters, right? So this pressure will be the gas pressure here. And we're told that the final pressure of the gas will match the external pressure that's gonna cause the compression. So that looks right. So it's almost like you put this pressure on the piston, put a pin in it, so then you say, okay, get ready, pull the pin. So it's one step, which makes it irreversible. There's no sand pile thing here. And this is gonna happen at 300 Kelvin. Now notice the difference. If you pull this and it squishes it super quick down to 10, the temperature of this gas is actually gonna go up a fair bit. But you're not allowed to take the final volume measure until this gas temperature bleeds out the heat. So it returns to 300. So it's like you're waiting for this temperature to come back to us. We let the heat flow out as necessary. So that makes sense. That's how it's not a constant temperature through the whole process. This temperature will spike, but then you wait for the heat to bleed out to reestablish 300. Okay, so that's fine. One of the things that I can't help, I can't help but think about is the work. Now, remember how the formula for work was P external dV? The external pressure is constant through this whole thing. So you can pull it out of the integral, and the famous formula for this one is that. So we could go 2.462. Well, I don't want to give away do the complete solution, but you can calculate this, and don't forget that if you're using atmospheres and liters, you might have to multiply that by that conversion, which is joules per atmosphere liter. So you will get an answer in joules here of work. And the volume got smaller, so it'll be a negative, it'll be a positive number for work. We did work on this by compressing it. In order for the temperature to stay the same, because delta T equals 0, initial and final temperatures are the same, and it's ideal, there's no potential energy of interactions that can do anything. It's only kinetic energy temperature changes that mean anything. So technically, the heat by default has to equal the negative of the work. Now, key point. Is this heat that's equal and opposite to this work calculated this way? Is it a reversible, or is it simply the irreversible and the actual heat of the process? This was not reversible. Even the work calculation that was done here was done on an irreversible calculation, so it's not reversible. This is the actual heat of the process. So one of the things we can do right away is the change in entropy of surroundings by definition. If you have it, what was the actual heat transfer? So that was a positive number for work, which means the negative of that, you'll get a negative number in joules for the system losing the heat. Surroundings is the negative of that value, so the surroundings will have a positive number of joules of heat divided by the temperature, which was 300. So that would give you your number for the change in entropy of the surroundings. And the funny thing is, change in entropy of the system by definition is a reversible quantity of heat divided by that, which, by the way, Q reversible. And we could have gone back to our problem A. And remember how I was drawing your attention to this one in the work formula. See the difference? So do you not see how in this case, because the work, the heat from the system is the negative of the work, we could have also said the change in entropy of the system, this is reversible work. That is also the heat of a reversible path. So we could have taken the heat of the reversible path, which was equal to the negative of the work, which equals this, and divided by the temperature. See how they cancel and you get that formula. So we already calculated the amount of heat on a reversible path in part A. So we can literally take the heat on the reversible path of the system from part A divided by the temperature, which is 300. So the change in entropy here will end up being the same as part A. So now the change in entropy of the universe will be the addition of the two. And we already know that this one in part A would end up being a negative number because we squished it. So we know that this was some kind of negative number. The surroundings received heat and its entropy would be a positive number. This is a spontaneous process, which tells me this answer, this number has to be bigger than that one so that you get a positive number, which means that it's a spontaneous process. If it's a negative number you got, then that means that this would not be a spontaneous process. But we can believe ourselves. You pull this pin, always the direction of spontaneous change is for this to go down. This process is spontaneous, and therefore the change in entropy of the universe, or the total, has to be a positive number, which it is in this case. So that is question 4.